away.
All right, thanks a lot. So, hi everyone. Yeah, my name is John Steinmetz, and I'm a PhD student at the University of Rochester in Andrew Jordan's group. I'm going to talk today about a project we've been working on with Irfan Siddiqui's group from UC Berkeley, where we've tried to develop a new method to, in a way, film qubits going through quantum gates by using weak measurements. And that can allow us to find out more information about any sort of time-dependent errors that are happening throughout the quantum gate. We've done it so far with single and 2 qubit gates, and the experimental group that we're collaborating with has actually taken some data now, so I'll have some of that to show you as well. Our research group right now, the Andrew Jordan group, is split between Rochester and Chapman University in California. I want to acknowledge my coworkers on this project. So on the theory side, in particular, Demolo Das and Tathagat Karmakar have put in a lot of work. And then obviously all of our collaborators at UC Berkeley who have done some really incredible work on this. All right, so to start, I want to talk about some different types of errors that you can have in a quantum gate. So the easiest one to think about might be a pulse error, right? So let's say you're targeting your qubit level spacing with some kind of pulse, and your pulse is the wrong shape. Maybe it's too small or too big, and so you over-rotate or under-rotate your coherent gate. And maybe you don't end up, if you're applying a pi pulse, maybe instead of going from 0 up to 1, you go 0 into some superposition that's very close to being a 1. You can also have crosstalk errors where you're attempting to target one particular qubit in your system, and accidentally maybe you target some of the others as well, or maybe there are some unwanted correlations between the targeted qubit and the others, especially the nearest neighbors. And another one, which is particularly important for the superconducting systems that we're looking at, is leakage errors. So with physical qubits, you often have a whole ladder of levels to them. You don't just have 2, right? And even if you try and target the 2 in the qubit subspace, you can often get coupling to higher levels. And so some of your qubit population can escape up into a higher level. So the traditional, or maybe not traditional, but maybe the easiest, or the first thought a lot of people would have on how to determine how well your gate is working would be to send your qubit through a gate, and you get a final state, and then you perform projective measurements on that final state. And you run this experiment many times, and you get some result each time, and using that you can estimate the final state and then calculate something like the fidelity between the state that you got and the state that you were anticipating. The issue with something like this is that you can't tell anything about what actually happened throughout the gate, right? You only see the cumulative effect of any error that's happened. So here are 3 pulses that have the same area underneath the curve. Right? So here we just have a simple under-rotation error, but maybe the pulse was a little bit lopsided like that, or maybe it was something totally crazy like this last one. And that information could be valuable and tell you some information about what's going on in your experiment that maybe you didn't know was there. So that's the issue with just doing a projective measurement at the end, is that it only tells you a cumulative effect. And something people do is to make projective measurements throughout the gate. And this does work, but what can happen is if you try to shut off your gate, right at the peak or something like that, you shut it off instantaneously. That's quite hard to do without introducing disturbances, transient effects into the gate. So what I'm proposing is to make weak measurements throughout the gate, which we run the entire gate, doing weak measurements the entire time, and that should give us some time resolution about these error pulses. All right, so to those of you who are unfamiliar with weak measurements, I'm just going to summarize that briefly. So we have a qubit in a cavity, and this is summarized by the Jaynes-Cummings Hamiltonian. So we've got a field component, a qubit component, and then the coupling between the field and qubit. If you work in the limit where this coupling is very weak, we call this the dispersive regime, and you can approximate the Jaynes-Cummings Hamiltonian like this. The only important part here is this factor, right? So the cavity field frequency gets shifted by this amount chi, which is dependent on the qubit state. So the frequency of the field will get shifted in a different direction depending on what state the qubit's in. And here I've got a visual representation of 3 different types of measurements. So over here is the one that we're probably most familiar with, right? A strong measurement or a projective measurement. So in that case, you have your so when you make a measurement, you get your 2 field quadratures, which in this case I'm calling I and Q, and you basically get a readout value that is drawn from one of these 2 distributions. So you'll get a number from up here or a number from down there. And by looking at that number, this is really simplified, but by looking at that readout value, you can basically tell which state your qubit is in, right? If it comes from the top distribution, then maybe it's in the excited state, and if it's from down there, then it's in the ground state. By engineering this weak interaction, we can cause these distributions to be heavily overlapping, and what that does is when you get a readout value, you can't say for certain which distribution it came from, right? You can maybe make an estimate, a probabilistic estimate, but you can't tell for sure. So what this does is it gives you a little bit of information, a hint about what state the qubit's in, and it also doesn't collapse the state fully. It only collapses the state by a small amount. And then here I've listed just to show the other limit, what we call a no information measurement. I think there might be a use for this. I'm probably going to ignore it, but I just wanted to show it as the other limit where these distributions are totally overlapping. There was no dispersive shift, and by measuring, making a measurement, you don't actually get any information about the qubit state. All right, so I'm going to show you what this looks like when you take many weak measurements over the course of a gate. And I'm going to show you this for a pi pulse, where we're continuously measuring the z coordinate of the qubit. So here's one sample quantum trajectory. So you can see it starts at the ground state, and after the pi pulse, it reaches the excited state, just like we would expect. Here's another one. The difference now is that we get a movie of how it got from the ground state to the excited state under the measurement dynamics. And this thing is stochastic because each time you make a measurement, and I think we're making about 200 simulated measurements in this picture. So each time you make a measurement, your state jumps. So that's a stochastic component in the trajectory. So in order to be able to get a good estimate of what the aerodynamics are, we're going to need to take a lot of trajectories. And if you take a lot of them and you average them, you do get a smooth curve, which sort of approximates the pi pulse you're expecting. But obviously, it doesn't quite get to the excited state over here, right? There's some extra decoherence that gets added in. So the way I'm going to try and pitch this is as an error mitigation technique, where you don't use the weak measurements if you're also trying to use your gate for some technical purpose and you need it to work precisely. I'm going to suggest that we use this method to diagnose an error, and then you apply some maybe correction pulses, and then you run your gate afterwards. So you can predict exactly what this smooth ensemble average will look like using a Lindblad master equation. So here we have the unitary dynamics. So we're going to assume the errors are also unitary for now. And then you have any sort of decoherence due to interactions with the environment or the measurement back action. The way we do this, so this is actually kind of a tough parameter estimation problem, because you have what is basically a set of equations of motion where you have an unknown parameter and it's time dependent. So just apart from all the quantum stuff, this is just a difficult mathematical problem to solve. So the way I've done this is using numerics. we basically perform these weak measurements. We look at the ensemble average, and at each time step, we estimate the error that would have caused the measured update in the z-coordinate. And since there are multiple different errors that can cause each update, we need to use many different initial states of the system. So for the case of a qubit, right, you have 3 block coordinates. You need to use at least 3 different initial states in order to pin down which kind of rotation is causing the update in the z-coordinate. Okay, so I'll show you first with some simulated data what this looks like. I'm going to start off with a relatively low number of trajectories, so 10 to the 5. And we can see that the averaged readout here is pretty noisy still, although you can see that, for example, the one starting in the negative z state does make it basically up to the positive z state. And we're starting from 3 different initial states here, so minus z, plus y, and plus z. The estimate over here, so this red curve is an error that I input on purpose into this data. And this is kind of a funny error because it's sinusoidal, and the integral under that sinusoid would be 0, right? So the cumulative effect of this error is almost nothing. You get fidelity being 99.999 whatever percent. But there's this actual huge error going on that you don't find if you just look at the final state of the system. So I think that's the power of this method, is that you can find errors maybe that don't show up in traditional methods. If we increase the number of trajectories a little bit, we get a smoother set of ensemble averages and a better error estimate. And if we keep increasing, we eventually get to a point where this converges perfectly to this time-dependent error. And obviously, this is simulated data. I'll show you some of the real data in a second. Okay, so first I want to talk about how do we choose how strong to make the measurement. Because as I said before, there's a trade-off where if you make the measurement stronger, then you collapse the state faster, but you get more information. So there's a trade-off between the information gain and the amount that you're disturbing the state. And so what I've plotted here is, again, from simulated data, a measure of the error in the estimate. So the error is really huge here, and there's this optimal point here. And along the x-axis here is a parameter tau, which we call the characteristic measurement time. It's kind of like the time it takes for the state to collapse. So a lower value of tau is actually a strong measurement, and as we move up here, that corresponds to a weak measurement. So if we make the gate, or if we make the measurement too strong, we get really good agreement at the beginning because you're gaining a lot of information very fast, but the gate collapses, or the state collapses rather, before the gate is done. So by the end of this, the algorithm is having a really hard time identifying what's happening. If we make the gate too weak, then it doesn't collapse, but it's relatively noisy the entire way through. So I'm going to suggest we pick a point around here, which is, in our simulations, it's generally, between half and 1 iteration of the gate time. So this dotted line is how long this theoretical gate would be. And in this case, we end up with something that is consistent, has consistent noise throughout, and it's sort of the smallest possible amount of noise you can get. All right, so now I'll show you some of the experimental work on this. We sort of acted in an advisory role with our collaborators at UC Berkeley, who developed this new 2-qubit sample. It involves, so we've got 2 transmons, and they're coupled with a parametric coupler that you can target in order to induce entangling interactions between the 2 qubits. Here we're going to focus on swap-like gates. And in particular, we were aiming to have a very high cavity loss rate so that you don't have memory effects in the cavity. Keep the system Markovian if we can. There are ways of tackling the non-Markovian case, but it's really, really difficult. All right, so here's a single qubit pi pulse, just as a benchmark. Eventually, we'll move on to 2-qubit gates, but here's a single qubit gate. So we used 6 different initial states here. And in each case, we apply a pi pulse about the x-axis. And the pi pulse we're applying has this particular shape where it has, I think it's a cosine ramp, and then it's got a flat top. So we filter this through the algorithm, and the dots on that plot are the estimate of the error. And you can see it follows the actual error that we, again, input on purpose into this test system. It mimics that error very, very closely. And it also finds out the direction of the error, right? It sees that there's this flat top curve in the x direction, and that there's 0 error, basically. There's some oscillations there, but it basically tells that there's no error in the y rotation direction. Okay, so now let's talk about an entangling gate. And this is a much more complicated scenario, because instead of having 3 block coordinates to track in a 2-qubit system, you have 15, right? You have 3 block coordinates for each qubit, and then you have these 9 potential correlations. So in an ideal situation, you would have maybe some idea of which interactions you're targeting with the gate, where the error might show up, so we're not having to estimate all 15 at once. You can estimate all 15 at once, which I'll show you what the data looks like. It's a bit of a mess. The gate we're looking at here is a square root I-swap gate. So what that does is it acts in the 0, 1, 1, 0 subspace and rotates between those two. The square root I-swap gate will take you halfway. So it'll take you from, say, a 0, 1 state into a superposition of 0, 1, and 1, 0. So here's one sample ensemble average. So qubit 1 starts in the excited state and moves into a superposition. Qubit 2 starts in the ground state, and so they both move halfway. Here's another one starting from a different initial state. And the full set of data here, we need more than 15 initial states. I think here they took 36. So here's the data. It's a total nightmare. But here's some of the results that we get from this. So I'm going to show 3 different examples. So here are 3 different types of swap interactions. So we have one that takes you the entire way, which is a full swap gate. And then you have 2 that are square root swap type gates. And we can see, so I'm only listing 4 of the potential coordinates here. So xx, xy, yx, yy, because these are the ones that get involved in this particular gate. And we can see that it tracks the correct direction and the correct shape of this error quite well. There are some oscillations in the data, obviously, which is due to the fact that we have limited numbers of trajectories, and we're using smoothing filters in order to get better results. But that can introduce some small oscillations. All right, so last thing, I want to talk about how we cover leakage to a 3rd level. So in this case, we treat the system as a qubit. So you have your qubit subspace, and then you have this 3rd level. And a qubit has 8 generalized block coordinates, right? We can generalize the block coordinates and the Pauli matrices and everything up into a 3D system. And the 2 field quadratures are analogous to 2 of those generalized block coordinates. And by using the same method as before, using a generalized Lindblad-Master equation, we can use the exact same method. Here I've shown an X rotation with an undesired leakage pulse. And here's some preliminary data showing that we can track separately that X gate and the leakage pulse. And it separates those 2 interactions into these separate curves. All right, so with that, I'll summarize. Continuous monitoring reveals the inner workings of a 2-qubit gate or a single qubit gate, right? We get a movie of the qubit going through the gate. This can help us diagnose many different types of error. We are also theorizing that this could be expanded to measuring decoherence and things like that. And this continuous method can avoid some of the problems that come in with projective measurements like these transient effects in gates, and also maybe can be used to measure time correlated errors and things like that that wouldn't appear otherwise. So with that, thank you all for listening.